Welcome everyone to this workshop on Hodge Theory, period mappings and local systems. It's good to see everyone. I just wanted to make one quick announcement. I think the videos from all the lectures will basically be available pretty soon after they're given, and I think you'll get a link, but then it'll also be available on the website if you want to go back and watch some lectures. Yeah, okay. And all right, so to kick things off, it's our great pleasure to have Hélène from Freie Universität. And she will be speaking about density of local systems with quasi-unipotent monodromies at infinity.
Thank you, Ben, and thanks to the organizers for the work, and to Virginie, and in particular to correct my mistakes. So thank you very much. So this, I have lectured already twice. It's very recent. The preprint exists, but it's going to be revised during the Christmas break, and only after that we will upload it on the webpage. So the title, I think, is quite clear. I have to explain where we consider the problem of density. I have to define what quasi-unipotent monodromies at infinity means and in which space we consider this. And then I have to tell you also, it's before I start the more mathematical lectures, that it is a sort of, so I chose a complex statement, you will see immediately, because of the title of the conference. And at the same time, it's a confirmation of a program we launched now like 2 years ago with Moritz. And so it comes easily, so to speak. It's not the hardest part of what we try to do by far, but on the other hand, it's a nice illustration. Okay, so I start here. And okay, and maybe I should look at, okay, at the time. So we do complex geometry here. So S is X, I apologize, it's a smooth quasi-projective variety defined over the field of complex numbers. So the topological space consisting of its complex points has a topological fundamental group, which is based at some chosen point here, X. So at some points, X will play a tiny role. So that's the reason why I wrote it. And we fix affine algebraic group scheme together with an embedding in GLR defined over a domain of finite type. So for example, we could take GLR over Z as an example. And so what's important here in the information is that it's a finite type. I mean, it's not affine in the sense, pro sense, but it's really a finite type. And associated to those data, first associated to G, we can define the frame moduli space of G representation of the topological fundamental group here. So the moment we talk on frame moduli spaces, then it was important to fix the base point here. So this is defined by the functor, which is written here, which associates to an affine R algebra, a representation, abstract representation, so it's no topology here, of this topological fundamental group. And then because we have generators relations, the moduli is fine, it's affine, it's defined over R. So standard example is either GLR, as we discussed, or if we want to fix a torsion determinant, so we take N here, which is invertible on our ring of definition, and we take the inverse image by the determinant of mu n. Mu n, that's a group scheme of roots of unity of order n. Is that okay? So for example, we could take n equals 1, we would have SL. So those are the data. So those are very classical data here. And the second slide here is yet again very classical data. So we will define what are quasi-unipotent monodromies at infinity in a slightly more general phrasing. But this extra generality which we put, it's really slightly more general, but the methods are the same. So it doesn't cost anything to present it like this. So we fix a normal compactification here. Of course, because our variety was complex, so we could fix a good compactification with a normal crossing compactification. But in view of an extension of the method in a more arithmetic situation and not in characteristic zeros, and it's it's maybe better to just fix a normal compactification because this one always exists, regardless of the characteristic. And then we have monodromy loops around the codimension 1 points at infinity in this given compactification. So they are not well defined in the topological fundamental group, but what is true is that their conjugacy classes are well defined. And so we define for a given A here, it's a bit of a shitty definition here because we are going to apply it for A being an algebraically closed field of characteristic zero, so then it's a good definition. So we define the quasi-unipotent A points of the Freie moduli here by looking only at those representations which have the properties that the conjugacy class of the monodromy at infinity is quasi-unipotent. I think it makes sense. Okay. And quasi-unipotent means that some power becomes unipotent, and unipotent you can define for the GLR in any with values in any ring by saying that this matrix -1 has to be nilpotent. Okay, so that's really a very easy definition. If you fix here, so you define that on GLR, and then you define it on the moduli, the Freie moduli of the group you started with, endowed with this embedding in GLR by just taking the intersection here. So, okay, fine. So now starts the lecture. So in those Freie moduli, so first we fix a prime, L. And we give ourselves a ZL bar point of the ring of definition of the Freie moduli. Okay. So we consider so this inclusion, which is written here. So we consider the QL bar points of the Freie moduli, and inside we have the ZL bar points of the Freie moduli. Now the QL bar point of the Freie moduli is very easy to understand. The points are just those abstract representation of the topological fundamental group based at X with values in GLR of QL bar. And then because it's fine here, it's a fine moduli. So we have the same definition for the L bar, for the ZL bar points. That means that's a point here, ZL bar point, it's a representation, abstract representation of the topological fundamental group with values in G of ZL bar. But because this group here is a finite type, is finitely generated, then it lands here, the value here is in G of finite extension of QL. And then once I have a finite extension of QL, if I request in addition that it is integral, so I land in the ring of integer of this finite extension of QL. And then this representation here factors through the étale fundamental group. So that means if I look at the ZL bar points here of those frame moduli, those are L-adic representation of the étale fundamental group. Is that okay? Why would we wish to look at those L-adic representation? It's because now all of a sudden, so I can say, I can switch the language. I can say it's an L-adic representation, or I can talk like that. I can say it's an integral point. But on those integral points, we also have a Galois action. And how? Which Galois group? Now, this is really the Galois group of the field of definition of the variety. And because I'm always going to look in the sequel at the Galois group modulo taking open subgroups, I may assume that I have a rational point here. So I have a field of finite type over Q over which X is defined. And then by passing to a finite cover, I may assume that I have a rational point of X over this field of finite type over Q. And consequently, Grothendieck's homotopy exact sequence for the étale fundamental group, linking the fundamental group of X now really defined over F and the fundamental group of X defined over F bar. And when I say fundamental group, I mean the étale fundamental group. The Galois group here splits by the choice of this X. So it's a choice. And via this choice, G acts via conjugation on the kernel. So the moment it acts, so G is the Galois group here of F, viewed as the automorphism of F bar in F for this given complex embeddings, which is part of the data. And therefore, G acts by conjugation here on the étale, the geometric fundamental group here. And consequently, it acts on the L-adic representations here. Okay, I didn't write the action, but if you have an L-adic representation which is written here, you assign to little g a value rho of g, and now if you have an element gamma in your Galois group, then the transformation of rho via gamma assigns to G just rho of gamma inverse times G times gamma. I mean, that's a classical action. I mean, the moment it acts on the group, it acts on representations. So this enables one to pose a definition. So when we have there's one thing I should underline here is that this frame moduli here, when we look at the points of the frame moduli with values in an algebraically closed field, and here a characteristic zero algebraically closed field, so QL bar, then I think of it as being an algebraic variety. I mean, a reduced algebraic variety, because I'm just looking at the points here. And then a closed subset is the Zariski closed subset. And one says that it is special if each, so because it was affine of finite type here, it's an Noetherian space. So any closed subset is a union of irreducible components. And then one says that it is special if each irreducible component meets the integral locus, that means the locus of étale representations, I mean QL bar étale representations. And in addition, S is stabilized by some open subgroup of the Galois group. So that means, if you like, if you can say in short, à la tête, it is integral and Galois invariant. I mean, up to taking an open subgroup here. And of course, because we have finitely many components here, irreducible components of S, the Galois group is permuting those irreducible components of S. So we can immediately remark that this definition for special, S is special if and only if its irreducible components are special. It's a small remark. So, and then the theorem, here's the first theorem, which I denote by theorem A, is telling us that if S is special, and you see, by the way, I can, before I discuss the theorem here, I can make a further remark here. I was telling you I'm looking at the Galois group modulo open subgroups. And in fact, it doesn't really matter what F you take here. I already say you can always make it larger and larger algebraic. You can replace it by a finite extension. So the theorem here is that if S is special, then when we regard, so S, I recall, it's the Zariski closed subset of the QL bar points. The QL bar points are topological points, most of them, but special means that they contain étal points, and then in addition, this étal locus is Galois invariant. And then the conclusion is that under this assumption here, if I look at the quasi-unipotent points inside of S, instead of the topological points, then they are Zariski dense. So that's the statement here. So you can say it's quite technical, but we will see immediately a consequence of the theorem, which is not technical at all, and which can be formulated just by half of a sentence. But before doing this, let me, let me first do this, and then I will tell you a heuristic. And it's very good that Carlos is here because he can interrupt me and correct me. So let us assume, in addition, now you remember G was our subgroup here, algebraic subgroup of GLR. Let us assume that it is reductive. So for example, let us take one of the two examples we had before, either GL or GL with a fixed torsion determinant here. And then, as we learned from Carlos' work, we can consider the categorical quotient here of the frame moduli by the action of G acting by conjugation. And this defines a map here, which is algebraic. So this categorical quotient defines an algebraic scheme. And this quotient map here is defined over R. And in addition, it stabilizes the quasi-unipotent locus, because the quasi-unipotent locus was defined by the very definition is defined by a conjugacy class. So it descends to the quotient here. So this enables one to define the quasi-unipotent locus now really of those Betti moduli. Let me call it Betti moduli here, of the Betti moduli. Why Betti moduli? Because if you take G equals GLR or SLR, then that's really the Betti moduli which appears in Carlos' foundational work. So that means the complex, those points here, quasi-unipotent points of MC, that's precisely the local, semi-simple local systems, which have a topological local system, which have the property that the local monodromies at infinity in the classical sense acts quasi-unipotently. So we call it the quasi-unipotent locus. And theorem B here, now with this very, now it's a more handy space here, is that the quasi-unipotent locus is Zariski dense. If you take the whole moduli space, the quasi-unipotent locus is Zariski dense. So that is easy to formulate. I mean, it takes not even half of a line here. And let me discuss a little bit a heuristic for the theorem B. With theorem B is the one with the standard notation here. So there is no frame moduli. I mean, that's really the moduli we are interested in. And yeah, maybe I should really underline, I said it, but let me repeat that if we take G equals GLN, GLR, or SLR, for example, or GLR with a fixed torsion determinant, the complex points here are really semi-simple complex local systems, even possibly with this given determinant here. So what is the heuristic here? So the heuristic is given only in those two cases here. So by the work of Carlos Simpson, we know that in any irreducible, in fact, I should say, no, irreducible component here is a mistake. I should say connected component. I apologize. In any connected component of M, there is a complex variation of Hodge structures, which is understood in his work as a fixed point under the C-star action, which is obtained by rescaling the Higgs field by C-star. Now, I'm not very precise here because Carlos' work is for X-smooth projective. But here we are talking of quasi-unipotent locus, which means that if we want some non-empty statement, we need a boundary. So that means we don't want X to be projective. But I was explained by Christian Schnell and someone else that the work of Carlos has been generalized in the quasi-projective case, but I don't have a precise reference here, so I just wrote Carlos. And if it's not completely written, someone should write it, so that should be the same. One should replace the Higgs moduli by the moduli of parabolic Higgs bonders and so forth. So the hope is that those coming from geometry are even Zariski dense. And why those coming from geometry? Because the theorem of Briscoe and Griffiths in complex geometry and Grothendieck in L-adic geometry is going to telling us that every local system which is coming from geometry has the properties that its monodromies at infinity are quasi-unipotent. So so let me go back here. Among those here, those points which are quasi-unipotent, we have the ones which are coming from geometry. Now, I didn't take a slide to explain what it means to come from geometry. I mean, by Delin's semi-simplicity theorem, we know that even a complex subquotient over Q bar of variation of Hodge structures, which is defined over Q, is in fact a sub. I mean, the category is semi-simple. And then you want this on the Zariski open of your initial variety here. Okay, so that's the heuristic why we would wish to have this theorem. You can say the same blah blah slightly differently to say that wishing that geometric points are Zariski dense. Because of this theorem here, in the non-proper case, this would be the same as saying that the geometric point in a moduli where we fix in addition the conjugacy classes of the monodromy at infinity, that's the same problem. We can fix the conjugacy classes of the monodromy at infinity, assuming they are quasi-unipotent, otherwise they have no chance to come from geometry, or we can look in the whole moduli, that's precisely the same problem. So this is a sort of reduction step here in a large program. I don't even say program, in a large, I mean in a big dream, so to speak. So I hope it clarifies here the formulation. So recall that the theorem B is the one which is easily formulated, I mean, which is really anchored in complex geometry, while theorem A here was the one which was more specific to formulate, because we need the definition of spatial. We need, we are no longer purely in complex geometry, because we are looking at L-adic system on complex varieties. So, so I explain here why the theorem, which is more difficult, I mean, the L-adic theorem here implies the more classical formulation here, because QL bar is algebraically closed in the formulation of theorem B, I mean the classical theorem. Let me go back to theorem B, which is here. I could replace C by QL bar, because quasi-unipotent for topological local system with values in GLR of QL bar or of C, that's the same thing, because to be quasi-unipotent is saying that the eigenvalues of the monodromies at infinity are roots of unity, and roots of unity are preserved by any abstract automorphism of the field, C or QL bar, and in particular, identification of QL bar with C. Okay, so that's one thing. So we may replace in the formulation C by QL bar. So now, because the quasi-unipotent points here have the properties that they are the inverse image by the categorical quotient map here are the quasi-unipotent points in the frame moduli here, it's enough to prove the same statement, but now on the frame moduli. So far I haven't done anything, this is just blah, blah. But just because G acts on the ZL bar points of the frame moduli, we have already half of the definition of the ZL bar points of M square here being special. The only thing which we need here to make it special is to be sure that we can find a L such that the irreducible components here of the frame moduli, and from it the irreducible components here meet I should say differently, the ZL bar point, excuse me, I should say differently, the ZL bar point meets each irreducible component. Those irreducible components, they are defined over a much smaller field. I mean, R was this ring of finite type. You take an algebraic closure of its field of fractions here, and the irreducible component of M box here, M square, are defined over this smaller field. And like, for example, a number field. But what you want is to find an L which has the properties that each irreducible component hits. I'm sorry, the ZL bar points hit each irreducible components. But we are doing now classical finite type geometry, Noetherian geometry. They are finitely many irreducible components. Now, our topological fundamental group is a finite type. So first we pick one row I in each irreducible components with coefficients here in this smaller field, like it's like a number field here. It's not always a number field, but think of a number field here. And now, because the topological fundamental group is finitely generated, then each of those representations, you will find a number field over which all are defined. And in addition, because you will have finitely many denominators because you have finitely many generators of your topological fundamental groups. If you remove them and you take a place outside of those finitely many places, then this one is going to do it. Okay, so that proves that theorem A implies theorem B. So then the problem is to prove theorem A. So let me show you again the formulation of theorem A. Theorem A is that if S is special, which means integral in the sense that it hits the irreducible components hit the integral locus, the étal locus, and in addition, it's Galois invariant in this loose sense here, then the quasi-unipotent points here are Zariski dense. So let us prove that. So maybe what time is it? Yeah, it's going to be done in advance because I stop after the proof here. That was here. So as we already discussed, the definition of special, whether you take S is special if and only if its irreducible components are special. So it's enough to prove the statement if S is irreducible. So let us do that. So here, the second line here just records the definition of G inside of GLR. So I record what is R here. And now we introduce this scheme here, which in fact is even defined over Z, which is a standard way. In fact, Wendelin proves finiteness of over a finite field, over a given finite fields, the finiteness of irreducible L-adic representation in bounded rank and ramification. This is precisely set up. So this idea ultimately, you can say, I mean, basically it comes from, it's older, but in maybe the context is quite close here. So, so you take, here's this scheme. The S here was the set in which S is moving is a finite set. Those, and it's a number of codimension 1 points at infinity. So it's an affine space here, a finite type, which is defined over Z. And it's interesting for the following reason, is because we have, once we have fixed our, I mean, the monodromies at infinity are not defined, but their conjugacy classes are defined, and therefore their characteristics, I apologize, their characteristic polynomials are defined. So, so there is a well-defined algebraic map here from the QL bar points of those frame moduli into the QL bar point of N. Why? Because one thing I forgot to say, I apologize. I mean, this map is defined, but in fact, more generally, we have, if we best change N here to R, which was a ring of definition of the frame moduli, then the characteristic polynomial maps here for the TS at infinity is defined over this, this R here. Do I say nonsense?
R minus 2, maybe?
No, not -2, no, -1. No, -1. Ah, okay, so there are two things. I say R, so I was thinking of capital R, but here it's not completely correct because the conjugacy classes of the monodromies at infinity are defined over an extension of capital R. So I should take what I say that the psi map, the map of the characteristic polynomial, is maybe not defined over the capital R we had at the beginning, but over this, this extension. That doesn't change anything for us. In particular, it's defined over QL bar. So that's number one. And also over ZL bar. This is integral. And now for your question, Dan, I think this was Dan asking. Now we have the little r. I apologize. There's a little r in the capital R. This is not r minus 2. This is really r minus 1 because it's a characteristic polynomial. So I don't assume the determinant is 1. And that's why we have GM here. So GM receives the determinants. That means the product of the eigenvalues. And the other factors here receive the symmetric functions of the other symmetric functions of the eigenvalues.
But
so
there are symmetric functions including the determinant.
Yeah, so so that makes R here. If I hadn't written GM, if I had written
Sorry.
Am I okay? Are we? Do we agree? And I
yes,
am okay.
I'm sorry.
Okay, thank you. But yeah, it's not so important. I mean, and it depends. I mean, if G is really smaller, for example, if G is SLR, I could shorten slightly the writing here. But at any rate, we have this map. Is that okay? And it's defined. So here, as I said, I made a small slope. There's a small sloppiness. So R was talking about is maybe a slightly larger R over which the conjugacy classes at infinity are defined. So monodromy at infinity. But this is integral because it's really defined over a ring. And so we define, so now we have a new space. It's really a very easy space. We define in this new space we define the torsion QL bar points. What are, so it's a definition, are what torsion and why is that? Because you can think of the QL bar points of n as being the set of monic polynomials with coefficients in QL bar. We all agree, right? And then I define the torsion points are being those monic polynomials with coefficients in QL bar, which have the property that their zeros are roots of unity. So that's why I call it torsion. Is that clear? Okay, so that's a polynomial with torsion roots. I should not write roots here, I should write zeros, I apologize. And then why do I do that? Because that's precisely those which have the property. I mean, our definition of the quasi-unipotent points here is precisely such that the quasi-unipotent points are the inverse image by psi of the QL bar torsion points of n. And consequently, the set I'm looking at, of which I hope it's going to be Zariski dense in S, this is precisely this intersection, that's precisely psi inverse of psi of S intersected with the torsion point of n now. I mean, QL bar torsion point of n. So, so that's good. I mean, that's good. That means it's going to shift the problem from S in M into psi of S in the QL bar points of N. But we are no longer in the same situation. There are two differences. So let me repeat. So our problem, we start with S inside of the QL bar points here of M box, which is Galois invariant and hits the integral locus, etc. And we shift the problem to the image via the characteristic polynomial map here in the QL bar point of N. So M box is replaced by N, and then S is replaced by psi of S, and then quasi-unipotent locus is replaced by torsion locus. But here we made a big difference because this psi of S is not a Zariski closed subset, and here there is no Galois action a priori. So I have to say something, and this comes now. I observe that Chavalet's theorem applied to this Zariski closed subset of the QL bar point of M box here is going to tell us that psi of S, so psi of S lies in the QL bar points of N, is constructible. So that is, of course, a very important information. And because if I take the Zariski closure, then first it's going to be an irreducible subvariety of the QL bar point of N. And in addition, psi of S is, I'm sorry, the Zariski closure here will contain a dense Zariski open set, which is just saying non-empty because it is irreducible, but which is contained in psi of S. In addition, what? In addition, because S contained, S was irreducible, contain integral points, then Z contains integral points. So we are quite good because now if we replace S by Z, we have the first part of our initial definition of special locus, which is fulfilled. So here it is irreducible, and it hits the integral locus of A non-trivially. So, okay, so we want to prove this. It's enough to prove this because of what I said before. Because again, the main point here is that Chavalet's theorem. Now I have to bring what is a substitution for the Galois action. So we can consider, now I come back to then here. So I put the GM then in the definition, because now there is a finite surjective cover here, which separates the roots. It's a Galois cover, but of course it ramifies when two roots come together. It is that defines the divisor of ramification. So H is finite surjective. And consequently, it's enough to prove that this torsion locus here is a risky dense in Z. It's enough to prove that if I take the inverse image of Z by H, which is finite, then the pullback, and I take the pullback of the torsion point of N, then it is a risky dense. But what is the pullback of the torsion point of N? Just by the very definition, because N was the locus, was the zeros of the polynomials were roots of unity, then the inverse image by H of this locus, this is precisely the torsion locus of T. Now, really, in the classical sense, it's a torus, and those are the torsion points. That's why I had chosen this terminology here, this notation. So we have to prove this. And now in order to prove that, we have to make out of this Z here, a sort of a special locus. That means we have to find a Galois action on it. And now this is a part which I don't explain because now it is published. On this Z here, there is an element in the Galois group, which Daniel Litt called the Bogomolov element, which has the property that it acts on the coordinates of this. I mean, it's not only a torus, but it's a torus which is endowed with chosen coordinates. And then this Galois group here, this Galois element, forgive me, has the property that it sends the coordinates to their q's power. So you can choose a q which does that. The q is a p's power. P is a prime number, which is not L. L was already chosen. And you can say that T. So this set here, H inverse of Z, and from it the integral locus is invariant under this sigma action. Now, so that you can define now, this line is useless for the proof, but just to show you the complete analogy with discussion before, you can say that on T, on the torus here, you define special loci in the QL bar point of T analogously. They should be Zariski closed. All components should meet the integral points, and they should be invariant under sigma n for some n natural number not equal to 0. And now the former, in fact, that's the first theorem we could prove here in this program. Then if we have a torus which is defined over QL bar, then the torsion points here are Zariski dense in special loci. So in particular in the torus itself, because the torus itself has a property that it is invariant under this Galois, this simili-Galois action here, and then it's irreducible and it contains the L-bar points. So that finishes the proof. So that's the end of the story here. And I can make two remarks. The first remark is, in fact, here, when we have a special locus in this sense, so let us recall, you look at the Zariski closed subset of a torus with values in QL bar, I'm sorry, of the QL bar points of a torus, which hits the integral locus and which is invariant under this Bogomolov element here, then the torsion points are Zariski dense, but more is true. Not only they are Zariski dense, but there are unions. The special loci are unions, I apologize, of translate by a torsion point of motivic subtorus. And motivic subtorus is first a subtorus. You can think of it in two different ways. You go, I mean, one way is just to think algebraically, to say that your torus is going to come via a morphism of algebraic variety from the character variety of rank 1 local system of a variety you map your torus to. So that's one way to think. Another way is that if you go to C, it's easier to formulate, is to say that what did I want to say here? That the subtorus corresponds to a quotient Hodge structure of the Hodge structure of the torus. And now torsion here, that's where the arithmetic is hidden, is real torsion. I mean, the sense torsion in a torus. So this theorem here is, of course, an L-adic version of the theorem of Carlos, which was telling us that if I take the character variety of rank 1 local system on a smooth complex, projective variety, I look at the Zariski closed subset in it, which via the Riemann-Hilbert correspondence is still a Zariski closed subset of the Durham moduli, a Durham character variety. Then this Zariski closed subset has precisely this shape. It's a union of translates by a torsion point of a motivic subtorus here. So that means this is a pendant, an L-adic pendant of the celebrated theorem of Carlos here. So this is one remark. And second remark is that why this proof here? So I gave one name here. I mean, the proof of the line of the finiteness of companion of L-adic local system over smooth varieties defined over FQ to a given rank and a given ramification behavior at infinity. And on the other hand, if so if we could prove the method of theorem A comes from our proof of the density theorem of TEM arithmetic QL bar local system of rank 2 on P1 minus 3 points over FP bar. So arithmetic local systems are those which are definable over P1 minus 3 points defined over FQ for some finite field FQ. Said differently, they are invariants. They are invariant under some open subgroup of the Galois group of FQ. And then if one could prove that those arithmetic, if you like, dimension 0 special loci are the residence in higher dimension special loci on this P1 minus 3 points in any rank for TEM in the modular space, which is then called Chenevier space of TEM arithmetic local systems. Then one could prove the Hard-Lefschetz theorem in characteristic P for QL bar, semi-simple QL bar local systems without the assumption that the QL bar semi-simple local systems comes from geometry or more generally, I mean, wishfully, not more generally, but in the present state of knowledge, more generally, if it has weights and those weights are pure. Under this assumption, this is a theorem of Deligne, Bellinson, Gaber, Bernstein, but without weights, we have the corresponding theorem in characteristic 0 over C using transcendental methods again in Hodge theory due to Carlos. but we don't have the theorem in general. And if we could generalize this theorem here to higher rank, then we would obtain the Hard-Lefschetz theorem. And but we could prove it in rank 2, which is completely useless in order to prove Hard-Lefschetz. And the way we proved in rank 2 is precisely the same thing, because it's just so the same method as the one I explained, but over a finite field, because here we look only at M representations, and then it is a case that the étale fundamental group here is spanned by the 3 conjugacy classes of monodromies at infinity. So then the method of proof we apply here is precisely in line with the method of proof we applied here. So I think I talked already a lot. Thank you very much for your attention. Thank you.
All right, let's thank Hélène. Any questions?
Yes.
Yeah, just speak right out. Yeah,
Just go.
Okay. Okay, so the remark in this page is, so are you using sort of a Manning-Mumford type result, or are you giving a new proof of a Manning-Mumford type result?
No, we don't use any Manning-Mumford type result. We really prove, I mean, the theorem as written here. So let me formulate the theorem here. It's not formulated here. It's just written in a wishy-washy way. So of course, when we are looking at L-adic local systems here.
The previous remark.
Ah, you mean this one? The theorem C here? Ah, no, this one, no, I apologize. This one, we don't use any such theorem. There's no, we don't use any such theorem. Once we have the L, we really do rigid geometry, if you like. There's no, we work with the QL bar point of this affine space. So there is no Manning-Mumford here at all. Maybe there's something to do with Manning-Mumford, but at any rate, the methods here have nothing to do. They are not the same.
So I have a question.
Please.
And is it possible to formulate this kind of theory for periodic local system? Periodic, not erratic, periodic.
Well, I mean, I haven't yet thought of what one should expect. Here, here we have a conjecture which we formulated precisely in this article here over finite fields.
Periodic.
Yeah, let me finish. I will answer your question, but let me start the answer. So we formulated a very precise question here. And let me formulate it. And after that, we can discuss your question. The formulation here is that when we are over P1 minus 3 points, and more generally over variety defined over finite field, then over FP bar, we can define, we fix a residual representation. That means a representation with values in GLR of FL bar. And then associated to this, there is a rigid analytic space, an L-adic rigid analytic space, which has been constructed starting from Maser, going through many people and ending with Chenevier, which have the properties that the QL bar points of this rigid analytic space plays exactly the same role as Carlos' affine moduli, Betti moduli spaces. That means they are semi-simple local systems, semi-simple L-adic QL bar local system. Now, in this Chenevier space, we define special loci in the same way as I did here. So that an extremely important property is that this Chenevier space is Noetherian. So we can talk on the Therian topology, we can talk on irreducible components of Zariski closed subsets. And we define those special loci as being Zariski closed subsets, which have the property. So now there is no longer a condition that they hit an integral locus because everything is integral to start with, so to speak. But they have the properties that the Galois group leaves this Zariski subset invariant or some open in the Galois group. The Galois group of the finite field, because the finite field acts on it, it sends one geometric LAD local system to another one. So this is a very precise, and then the, I apologize, then the conjecture is that the arithmetic local system are dense in those special loci. Now, to even start formulating an answer to your question, one should have a parameter space for the p-adic representations. And that I don't know, maybe there is something like this, but I don't know that. I mean, my knowledge stops here with Chenevier in a long thread, starting with Mather, Taylor, Walsh, etc., etc., and at the end Chenevier. But for the p-adic representation, I don't know of a moduli space for those. So that's number one. Number two, usually one considers p-adic representation on p-adic varieties. So then we lose the spirit of what we do here, because even if I was over C, at the end, the method was to come to Galois invariant subspace. And what is, so we have a space, we have those moduli. And what is a Galois group? That's a Galois group of this field of finite type in characteristic 0 on which the variety is defined, or over finite fields, the Galois group of the finite field. So we have a field of finite type to start with, to talk on Galois invariant subspaces. So we have a space, and we have Galois invariant subspaces. Now here, I assume you have in mind p-adic varieties. First, I don't have a space, and then the Galois group is way too small. I mean, it's not a big Galois group like we have when we have a field of finite type. So I'm not sure. I mean, the setup, just so to speak, an analogy word by word would not work, which is not to say there is no analogy, but and I should think, and in particular, I don't know what should be true. I mean, here we are guided in all this work here and the theorems and the formulation of the conjecture, we are guided by something which is existing. We are guided by Carlos Hard-Lefschetz theorem. So Carlos Hard-Lefschetz theorem exists, is true, whether or not you have a variation of Hodge structures or new coefficients. It is for just the condition is semi-simple. It's in fact if and only if. So that means the condition is not a motivic condition, it's an algebraic condition. So so that is a guiding line which avoids making mistakes, so to speak, in the formulation of the problems. But here for the p-adic local system on p-adic varieties, I'm not sure what would be the guiding line, because I would be on a rigid variety, and what would be the guiding line. So I don't know. I mean, there is probably a formulation, but I haven't thought. So, okay.
Thanks. Yeah, thanks. Yeah, thanks. Yeah. I will try to think about what you said.
Sure. You tell us, yeah.
Yeah, absolutely.
Yeah, thank you very much. Yeah,
yeah thank you.
So Hélène, at the beginning you said so the quasi-unipotent statement, the density of the quasi-unipotent points is sort of on the way to understand when the geometric points are dense. So what do you have a plan, a vision, a guess
And I mean, over C, I could not, I mean, it's very hard. You should ask Carlos, but over a finite field where I have a better feeling of, I cannot prove it, but I mean, here over C, it is telling you again, I mean, once you know they are dense, if you dream of having the geometric points being dense in the whole moduli, it would be the same as asking for the geometric point to be dense in the moduli where you fix the conjugacy classes at infinity, quasi-unipotent conjugacy classes at infinity. But once I have said that, I don't know where, I mean, of course, then you have the work of Carlos. He's going to tell you that, I mean, the characterization of complex points, you can, I'm sorry, complex variation of structures, you can think of that as being an algebraic notion once you go to the Dolbeault moduli. On the Dolbeault side, on the Higgs side, what corresponds to a complex variation of a structure is a purely algebraic notion. But you have those C star fixed points, but among those C star fixed points, where are the geometric ones? I really don't know. What I prefer to think about, because I don't know, is Daniel also has a similar way of thinking, is to replace the complex points by the QL bar points. And then to look, then you have inside, you have the L-adic points. I explained that already. At least when the moduli are fine, that's why you have to go to the frame moduli. Then you are looking at the ZL bar points. And then for those, you are looking at those ZL bar points, which have the properties that the corresponding L-adic local system descends to a field of finite type. I mean, it's defined over on X over C, that means on X over F bar for F a field of finite type, but you want your L-adic local system to be defined on X over F, or some extension, some finite type extension of F. And that's the reason why I think like this, because I mean, in fact, it's already discussed by Carlos in his seminal article, because he's talking on, he proves that rigid local systems have the properties that they descend when you look at them as L-adic local system. At the time, he didn't know it was integral, but you have enough places for which it is integral. So you have L-adic local systems. And then he already proved that they descend to a field of finite type in characteristic 0. So I prefer to think like this, because at least we have a method, we have a Galois group, we have something in the hands. But over C, I don't have anything to characterize geometric. So you could dream for the L-adic local systems that they are geometric, if and only if they descend to a field of finite type, and maybe you add something like Durham at the place L, or I mean some L-adic Hodge theory in addition, or maybe not. So at least you can formulate questions. But for C, if I stay with C, I cannot even formulate a question, reasonable concrete question. So yeah, so yeah, I'm sorry, I'm quite limited here, because I don't know how to formulate the thing. So that's why I went with Moritz in this direction, because at least we could say something. We could try to say something with Moritz and with Michael, because the work on rigid local system, it comes from the same philosophy, so to speak. Yeah.
Okay, why don't we stop there? The Zoom room will continue to be open until the next talk, so you can, assuming she's amenable, continue asking Hélène questions. But let's just thank her again for the great talk.
Yeah, thank you. No, I should thank you. Thank you.